Hey guys, and welcome to this video about going a little deeper into the idea of multiplying radicals and rationalizing the denominator of fractions. And so this kind of stems from the fact that we just discussed how to multiply binomials by one another, or in general, polynomials by one another. So for example, the binomial 2x plus 4 times the binomial x minus 3. And we went into length discussing how to do that. And what we're going to do is we're going to take each term in that first binomial and we're going to distribute it and multiply it by each term in the second binomial, and we'll sum up the product. So for instance, I think we'll end up with 2x squared minus 6x, and I'm just color coding so you see exactly where we got these, plus 4x minus 12. And just collecting like terms, I think our final product is going to be 2x squared minus 2x minus 12. Awesome. And now my claim is that the strategy we used there, multiplying two binomials together, two polynomials together, is going to be the exact same thing when we multiply radicals together. And note how similar these two examples are, right? X is just a number, right? It's a number here and it's a number there. We just don't know exactly which number it is, but we can still carry out this multiplication. Well, the square root of 5 is also a number. Is it a very easy number to write with a decimal? No. So the best way to write it is the square root of 5. And so just like we have in this example, here we've got 2 times a number plus 4. That, whatever this whole number is, that's being multiplied by some number minus 3. You know, the square root of 5 minus 3. And we're going to multiply these two radicals in exactly the same way that we multiplied these two binomials. We're going to take that first term, namely, or that first, I'm going to say that first number, right? We talked about terms and numbers being almost interchangeable in our definitions. So I'm going to take this first number, 2 times the square root of 5, and I'm going to multiply that by the square root of 5 and negative 3. And then we're going to take that second number, 4, and we're going to multiply it by the square root of 5, and we're going to multiply it by negative 3, and whatever we get, we're going to sum them all up. So here we go. So I think we're going to end up with, and I'm going to take my time right here, really do it all out and show every single step that we do. So 2 times the square root of 5 times the square root of 5. So 2 times the square root of 5 times the square root of 5. And then we're going to have minus 6 times the square root of 5. Okay, moving on. Now in red to color code, we've got 4 times the square root of 5. And 4 times negative 3 is negative 12. Awesome. Okay, so woo, we did our first round of multiplication. Now let's see if there's any combining or simplifying we can do. The first thing I noticed right here is that the square root of 5 times the square root of 5, by definition, is 5. So here we've got 2 times 5, also known as 10. Negative 6 times the square root of 5 plus 4 times the square root of 5, we can combine these to make negative 2 times the square root of 5. And then, of course, we have minus 12. And this 10 and minus 12, we can combine those two and we end up with negative 2 minus 2 times the square root of 5. And this right here, that is our product from that multiplication problem. I'm sorry that my writing has gone a little bit all over the place, but alas, luckily we have this digital device that lets me do something like that. Awesome. And so that's the strategy for multiplying radicals. It's really no different from the strategy for multiplying binomials. We just have a number plus a number, that whole quantity, times a number plus another number, or minus another number. All right, so I'm going to walk you through one more, and then I'm going to have you try these two on your own. So here, oh boy, this is gonna be tough. I might have to make this a little bit smaller. Okay, awesome. Here we go. So, starting with the, I'm actually going to zoom in to make sure I have enough space here. All right. So 2 times the square root of 3 times both of these bad boys. So we've got 2 times, well, I'm going to do a little, 2 times 3 is 6 actually. So we've got 6 times the square root of 15, right? The square root of 3 times the square root of 5 is 15, minus 2 times, and I know I'm doing this a little bit faster, the square root of 3 times the square root of 3 is 3. So, oh, okay. All right, moving on now to our blue rounds of multiplication. So 4 times the square root of 5 times 3 times the square root of 5, we're going to end up with 12 times, well, the square root of 5 times the square root of 5 is 5. And 4 times the square root of 5 times the negative square root of 3, we're going to get negative 4 root 15. All right, so let's do some simplifying. I think that we have negative 6 plus 60 for a grand total of 54. And then I think we have 6 root 15 minus 4 root 15 for a grand total of plus 2 root 15. And there's our product right there. And note to self, what's kind of interesting about these radical multiplication problems is every once in a while these radicals turn into a nice rational number. Like they did here and here and here, and that's really cool. Is it always going to happen? No. Is it sometimes going to happen? Yeah. All right. So I want you to pause the video and I want you to try those two problems on your own right now. Alright, so when we're all said and done, our product from the first round of multiplication was negative 48 minus 14 root 6. Of course, you could have said negative 14 root 6 minus 48, but people tend to like it in this order. And in the second round of multiplication, you see that there wasn't a whole lot of simplifying to be done when we did all of those 4 steps of multiplication. We ended up with 4 separate terms, none of which could really be combined. And you know what? Sometimes that's going to happen. Okay, moving on. So what I really want us to do now is I want us to go through a whole bunch of multiplication problems. And you'll notice that there's something similar about each one of these multiplication problems. Note, 4 plus the square root of 7, 4 minus the square root of 7, 3 minus the square root of 5, 3 plus the square root of 5, 5 plus 2 root 2, 5 minus 2 root 2, right? 2 root 5 plus 3 root 2, 2 root 5 minus 3 root 2. And what I want you to do is I want you to do all 6 of these multiplication problems, and I want you to see, as you make your way through, do you notice a pattern arising? And perhaps you can utilize that pattern to anticipate what the product is going to be, even before doing it, but still do it out just to make sure. So I'm going to ask you to pause the video, take care of these 6, and then play the video, and we'll see what happens. Alright, so hopefully, perhaps you started to note a pattern as you made your way through these. And perhaps you connected this to a lesson that we learned earlier in the year. Specifically, whenever we multiply, we were talking about polynomials at the time, but it totally applies here. Whenever we multiply two factors that look like this, a plus b times a minus b, we remember that the product will always be of the form a squared minus b squared. And that is exactly what happened in every single one of these cases here. For instance, in our first example, this multiplication problem definitely fits this form, and the product was 4 squared minus the square root of 7 squared, which is just 7. Oh, and that's why we ended up with a nice rational number 9. Here we ended up with 3 squared minus the square root of 5 squared. So 9 minus 5, 4. Oh, very interesting. Here we ended up with 5 squared, 25, minus 2 root 2 squared. And if you were to multiply this by itself, 2 times 2 is 4. The square root of 2 times the square root of 2 is 2. 4 times 2 is 8. Oh, that's why I ended up with 25 minus 8, 17. So, oh, interesting. Whenever we multiply these kinds of pairs of numbers together, involving the same two kind of numbers but separated by either addition and then subtraction, we end up with a rational product. A nice, in this case, integer product, which is really, really powerful stuff. And by the way, these pairs of numbers, they're called conjugates of one another. Like 3 plus root 6, root 3 plus root 6 and root 3 minus root 6, these guys are conjugates of one another. 4 plus the square root of 7 and 4 minus the square root of 7, they're called conjugates of one another. And one of the properties is that when you multiply them together, you get this awesome, nice, rational number. There are no square roots anywhere in the products for any of these. Interesting. So I'd love you to take this property, and why don't you try to just very quickly, oh, never mind. I thought I was going to have you do some more practice problems, but maybe we'll save that for the problem set. Okay, now let's use this to our advantage. I want to revisit the concept of rationalizing the denominator. Remember that in general, we really don't like having irrational numbers in the denominator of a fraction. Right, the square root of 7, it's a number, it's fine, but it's really not a very nice number, and we really just don't like to have that in our denominator. It makes it kind of hard to work with this fraction. So we much prefer to not have an irrational number in our denominator. We like a rational number like 2 or 3 or something like that. So how do we rationalize this denominator? I hope you'll remember, and if so, please pause the video and do it, but I'll remind you. In this case, we would take this fraction, we would multiply it by 1, right? We can't change what this fraction is, we can just change what it looks like. So we're going to multiply it by 1, meaning the numerator and denominator are going to have to be the same, but we're going to multiply by the square root of 7 over the square root of 7. Why? Because by definition, the square root of 7 times the square root of 7 is 7. And that's awesome. Now we have a nice rational number in our denominator. We're feeling good about it. And then in our numerator, yes, we have the square root of 7 up there, but we would prefer it in our numerator than in our denominator, just because it's going to be easier to work with. Kind of the same idea here. In this case, we're going to try to multiply by the same numerator and denominator to manufacture the cube root of something that actually is a perfect cube down here. And the nearest multiple of 32 that's a perfect cube, I think, is 64. So if we can attain this, we're looking good. So let's multiply by the third root of 2 over the third root of 2. 6 times the third root of 2 all over 60, the cube root of 64. The cube root of 64 is 4. And we can reduce this fraction right here to 3 over 2. Awesome. So that was all groovy. Now the difference between these two fractions and the fractions down here that we're going to explore now are, well, these guys have only one number in the denominator. Right? Here's the square root. Here's the third root. That's it. You're done. In these fractions, our denominator is a lot more menacing. It involves two numbers being added together, one of which is irrational. So if the square root of 2, that's an irrational number. It's a decimal that goes on and on forever. It does not repeat. 3 plus that irrational number is also going to be an irrational number. And we do not want an irrational number here. So here's the deal. What are we going to do? How are we going to multiply this fraction by 1, same numerator as denominator? How are we going to multiply it by something and get a nice number down here, like 7 or 18 or any nice integer? Well, we know from our exploration that we just did with these conjugate pairs is that if we multiply 3 plus the square root of 2 by its conjugate, we're going to get a nice rational number here. So let's multiply by 3 minus the square root of 2 over 3 minus the square root of 2. And now you can take your time in the side to do the multiplication, the 4 steps of multiplication for these two. But I know that when we multiply these two guys together, we're going to end up with 3 squared minus the square root of 2 squared, or 9 minus 2 for a grand total of 7. 7 is going to be our denominator. And it's like, wow, check it out. We got a nice rational number for our denominator. Our numerator, whatever, 5 times the quantity of 3 minus the square root of 2. And feel free to distribute this if you'd like. I would say weight in general, because you never know when these guys will be able to simplify. So it might make your life easier to weight just a little bit. And that's the jam. When we have a sum or a difference involving irrational numbers in our denominator, then go ahead and multiply by the conjugate, and that's going to end up giving you a nice rational denominator. So in this case, let's multiply by, and I'm going to zoom in a little bit just to give myself a little bit more space. Let's multiply by the conjugate being 4 plus the square root of 5. 4 plus the square root of 5. And I have done this a lot, so let's see. The product here is going to be 4 squared, which is 16 minus the square root of 5 squared. So 16 minus 5 for a grand total of 11. And one more reason why I like to weight to distribute in the numerator is that we see here, oh, we've got some nice simplification that can be done. We can write this as 3 over 1. So our final simplified version is 3 times the quantity of 4 plus the square root of 5. And feel free to distribute now. as 12 plus 3 root 5. And check it out. I mean, look at that. I love this way more than I like that. And so you see how this process of rationalizing the denominator can be really, really beneficial. There is no way that I'm going to be able to do this problem in the space provided, so I might have to copy it somewhere else. Give me a moment, would you? All right, we manufactured a little space. Same exact problem, I just kind of moved it down here. And, all right, here we go. Once again, this is the last one I'm going to walk you through. We want to multiply this fraction by some form of the number 1, same numerator, same denominator, such that we're going to end up with a rational number in our denominator. So we're going to multiply, in this case, by the conjugate of 5 times the square root of 3 minus 3 times the square root of 10. And the conjugate is namely 5 root 3 plus 3 times the square root of 10. 5 root 3. Of course, we must always multiply by some form of the fraction 1. Okay, our denominator, we're going to end up with 75 minus 30? No, minus 90. So, and you know, I've done this a whole lot, so I can do this kind of mentally, but you might want to write it out just to be safe. I just squared this guy, and I know that we're going to end up subtracting the square of this guy. Okay, so our denominator is negative 15. Not so bad. And our numerator, 6 times this whole bad boy. Oh, I know I'm being very lazy here, but please forgive me. Oh my god, that was so nice. Awesome. And check it out. We can do a little simplifying here. These reduce to, let's see, 2 and 5. Of course, we're going to still have a negative 5, if you will. So I think our final result, our final product will be, I'm going to go ahead and distribute this 2 as well, is, let's see, 10 times the square root of 3 plus 6 times the square root of 10. All of that over 5, and I'm just going to bring that negative out in front because I prefer it there. But boom! And listen, I know that we can't say that this is incredibly appealing, but alas, this, because it has a denominator of 5, it's going to be a lot easier to work with than our original fraction. So what I would like you to do now is take a moment, please pause the video, and please try to rationalize the denominators of all 3 of these fractions. And then when you're done, play the video, and we'll see how it went.